So this is streaming live on YouTube, so many others can actually join. I thank Abhishek for accepting to deliver a talk, and I'll just talk a little bit about. He works at Marine Biological Labs, which is a workhouse for microscopes and imaging. I will not repeat his bio so that most of them. It's already there on the posters and everywhere. So in short, Abhishek is a rising star in optical microscopy, and specifically in light sheet microscopy. He has expertise, huge expertise, I would say. And he's a Chan Zuckerberg imaging scientist, which is a distinction in itself. Currently his lab focuses on multi-view microscopy, light sheet, detail, super resolution, whatnot. I think everything that's available on Earth he works on, and quite a advancing kind of lab. Okay, so I'll just ask Abhishek to enlighten us with his work and talk. That's what. Abhishek, it's over to you.
Thank you so much for such a kind and kind introduction and overwhelming endorsement. I mean, that means a lot. I'm humbled and I'm grateful. I take your words, but I'm nowhere close what you said, but I'll try my best. Let's leave it there. Good morning, everyone. I'm joining you all from East Coast, so it's close to midnight here. But I'm glad that I'm able to join you all and talk to you some of the latest developments about light sheet. But before I start, I also wanted to thank Professor Mandal and his team for organizing this workshop. And I mean, I really think light sheet field has exploded, and it's very timely to do such a workshop. And I can't think any better place than Indian Institute of Science and Mandal Lab to host this workshop. So thank you all for organizing this and giving me the opportunity to discuss some of the aspects of light sheet. Unfortunately, I can't be there in person because of other commitments, but hopefully next year we will have chance to meet and be there in person. I will look forward to it. So I think some of the aspects I'm going to cover probably you all know by now, because yesterday Professor Mandal, he gave a great talk, and both advanced research as well as some basic introductory concepts. So please forgive me if it's too redundant, but I try to tailor a little bit so that I can focus more on biological applications and also discuss with you some building blocks of light sheet microscopes. And so basically, I mean, overall goal is at the end of this workshop, probably you all would be in a position to dissect any light sheet system and also figure it out which one is more suited for your particular application, whether you are doing biology or material science or optics. Because I would say there is no one microscope which can do everything we want. And that's the reason why we all keep tweaking, keep adding, and keep tailoring some of these technologies to meet our specific needs. Even though, I mean, you can argue that fundamentally all the optics and optical concepts are same, but still there are different implementations, different variants, and each one has its own limitations and flexibility or capabilities. So there is no one system which can meet all our requirements. So, and we will go through different variants of light sheet system. Unfortunately, I won't be able to cover everything because there are so many by now, but I'll try to give you a glimpse of broad groups you can subdivide this field. And I'm not going to cover in my tutorial talk applications related to material science, because Professor Mandal talked about that yesterday in a very, he gave a very good lecture on that. So I'll stay away from that. Sorry, I can't see you all in this classroom, but feel free to stop me. It's more like tutorial talk where we can have discussion. You can put your questions in chat and somebody can shout at me, or I can read your questions, and we will go from there. So let's keep it very informal so that we can have active conversation and discussion rather than me just showing you a bunch of slides and speaking from here. Let's double check. Everybody can hear me in this classroom?
Yes,
Can
Abhishek.
some? Okay, great. So here on my first slide, you can see this is example. This is a C. elegans embryo, and this is a good example, in my opinion, to stress why we need a system like SPIM or light sheet, because these embryos are very delicate, and as you can see during this development, they also start moving fast. So basically, for many biological applications, we need to acquire these images fast. We want to be gentle so that we can image some of these biological samples live without perturbing their development or whatever we want to investigate. And the other aspect is, for many applications, we want more isotropic resolution, whether it's for visualization or for finding blobs or cells or nuclei, or for tracking in a 3 or rather 4-dimensional. 3 dimensions are space and 4th dimension each time. So we will talk about that, how light sheet microscopy or this modality enables us to do such imaging. And also I'll discuss what are the limitations. That's important for us to understand for 2 reasons, because if we understand limitations, then we won't get very ambitious, and we will design our experiments, biological experiments, centered around that. And the other reason is a lab like Professor Mandal and all, they can come up with a better design or better microscope to solve or push this envelope. So for both reasons, it's important for us to understand what are the limitations. So let's go, let's see. Okay. I just wanted to put this slide not to overwhelm all of you, but there are more than 130 acronyms by now. And this is compiled by our Emmanuel. And that tells you that when SPIM or light sheet systems took rebirth in 15 years ago, suddenly this field has exploded. There are so many different variants people have developed for specific applications, and there are so many acronyms. We just hosted a light sheet conference and workshop last week here, and for fun, we did this acronym quiz game where we said acronym and we quizzed people if they can come up with the full description or full name of that microscope. And by and large, it was very difficult because there are so many acronyms and we can't keep it straight. So, but this illustrates that how this field has exploded, how many options we have. And there is a good reason for that, why we are all invested so much in this modality. So just to refresh your undergrad optics a little bit of your microscopy, and I'm sure Professor Mandal covered that yesterday. So typically when we do imaging, specifically fluorescence imaging, what we do, we illuminate our sample with a LED or a laser light, and we excite some of these chromophores, whether it's a fluorescent protein or dye, and we look at that emitted photons at red-shifted wavelength. So what's problem with wide field microscope? So one of the limitations with the wide field microscope is you end up illuminating your entire sample. So if your laser is going to travel or LED is going to travel through your entire sample, it's going to excite photons. And some of those photons make their way to your detector. So in optical microscopy jargon, what we say is you will have a lot of out of focus light. If your sample is very thin, it's thinner than the depth of focus of your lens, then you are fine. But if your sample is thick, those out of focus light, they degrade your image quality. So for a lot of, as you know, most of us, we want to do for many applications, three-dimensional imaging. We want to get the 3D picture of biological specimens and with time. So that's a fourth dimension. So what we want is we want to reject our out of focus light as much as possible so that each slice, each image can be as good as possible. The other thing, again, this is just to refresh your memory. I mean, I'm sure you know by now all these things. So there is a working distance and numerical aperture. So if you start increasing numerical aperture of lenses, basically your working distance starts decreasing. And why we need high numerical aperture lenses? Because if you want to capture more light and also you want higher resolution, you need to utilize or you need to capture large angle of those emitted photons. And this is very important. We will come back to this later. Why, what role working distance plays in case of light sheet microscopes, and how in many cases it limits our ability to use high numerical aperture lenses in a light sheet configuration. So basically our wish list is we want 3D imaging, we want high resolution, we want minimum phototoxicity, and we want to acquire as fast as possible. So these are broader criteria for doing live imaging. So what are the options we have? Certainly a confocal microscope is best choice, and you can go to any lab and probably you can find a confocal microscope or a variant of a confocal microscope, because it works well, it's well tested, and it's easy to use, and it gives you great optical sectioning. What we call is basically it rejects out of focus light pretty well. But one of the limitation of most of these confocal microscopes are imaging speed. They are relatively slow compared to the era we are living now. I mean, 20 years ago, probably they were pretty fast, but now as technology is developing and getting better, computational capabilities are getting better, detectors are getting better. Some of confocal implementations, it appears slow. So that's one of the limitation. And the other limitation is phototoxicity. As you know, in confocal, you use same lens to illuminate your sample and collect fluorescence. So your light travels through the entire sample, even though you are collecting information from a very small voxel or volume from that sample. So here is example. Basically, if you are wide field, you are illuminating entire sample and you are collecting fluorescence. So basically you have a out of focus light, and wide field, you are capturing the entire plane at once. So you are fast, but you are getting a lot of out of focus light, and phototoxicity is higher. Let me make it very clear. There is no, it's not easy to define absolute phototoxicity. So it's all relative terms, and there are a lot of factors they govern phototoxicity. It depends on your probe, it depends on your sample prep, it depends on your laser intensity you are using, kind of information you are trying to extract. So let's keep it in a relative terms, not in absolute term. So what we do in selective plane illumination. So in selective plane illumination, you can imagine, can we shrink this illumination into a thin plane? And you can see in this schematic, it's a wide field detection, but what you can do is you can shrink your illumination to a very thin layer or thin slice of your sample. And to get a 3D, either you can optically move your illumination and detection, or you can keep your illumination fixed and move sample through that. So you can get a 3D. And what it does, it only allows you to illuminate the region you are collecting information from. So it helps in two ways. It minimizes your phototoxicity because you're not illuminating or bombarding your sample everywhere with your laser light. And also it gives you selectivity, because since you are illuminating only region you are collecting information from, so to begin with, there is no out of focus photons to degrade your image for that specific slice. So that's basically a whole idea of selective plane or light sheet microscope, to synthesize a way to illuminate your sample so that you can illuminate in a plane selectively, and you can control where you want to uh, have your illumination and collect photons, emitted photons from that specific thickness or layer to build a three-dimensional image. And in this geometry, you can see, because you are collecting entire plane at one go, so you are not sacrificing your speed. So basically you are maintaining your speed, but you are minimizing your phototoxicity and photo bleaching by shrinking or confining your illumination in a plane. So does that make sense? Okay. And you can see in this schematic, this is your, you can call it confocal or wide field. Your laser is traveling through the entire sample and it bleaches this. It's a little exaggerated, but I hope you get this message across. While in plane illumination, you are just illuminating some specific plane, as you can see in this. So you are doing this photo damage or photo bleaching in only that specific reason. So basically this approach gives you fast imaging speed, but at the same time, you minimize phototoxicity and photo bleaching. And that's why it's so powerful. Again, this slide is very redundant. Yesterday, Professor Mandal talked about the history of light sheet. The first use, as if you recall your from your lecture yesterday, was demonstrated in 1903. But after that, there was a significant gap. And again, this approach took rebirth in 1993. And there were a few applications. But the field really exploded. Some work from Tim Holly's group and also Ernst Stelger's group in 2008, where Stelger's group, they showed that one can image using this approach a developing embryo for long time. So basically, you can capture the development of an embryo during this embryogenesis. And Tim Holly's group also, they showed that since it's fast, you can capture some neural dynamics. And basically, then we all realized that this technology could be powerful. And around the same time, also fast Cmos detectors for imaging came into market, and that has kind of enabled us to do push the limit of imaging as far as the speed is concerned, and you can get a large chip. And we'll talk a little bit about SCMOS camera later in this talk. So, and now you can imagine that now there are 50 different variants of home built systems and also almost 20 commercial systems available. So that tells you in fact, 5 to 8 years, this field has really exploded. And now applications are ranging from cell biology, single particle tracking, lithography, as Professor Mandal showed yesterday, trapping, to all the way to neuroscience or imaging corals, developing corals. So there is a broad range of applications now being demonstrated using this modality. So it's very powerful. So the question is how to create a light sheet. Probably you might have done already in your lab yesterday. You can take a collimated beam, pass it through a cylindrical lens, and basically you confine that energy in a plane, and you get a nice sheet-like illumination. Other approach is you can take a Gaussian beam and scan it fast along one dimension. If you can do it faster than what your detector can perceive, basically virtually you are synthesizing this plane-like illumination. And Philip Keller and all, they coined this name digital scan light sheet. You can also take 2-photon beam, and you can do the same thing. Scott Fraser and later on other groups, including Kishan Dholaki and all, they showed that you can also do 2-photon light sheet. Francesca will also talk. She has done, she's one of the early inventor of also this 2-photon light sheet. And then there are some non-linear beams. Basically, you can take Bessel beam. So why we want another beam? We have Gaussian beam, we have a cylindrical lens, or we can synthesize this virtual slit illumination using a Gaussian beam. So why we need non-linear beams? The reason sometimes you want non-linear beam, as you know, Gaussian beam converges and diverges. So depending on what is numerical aperture of your beam, you can have a certain Rayleigh length. So part of that close to beam waist, you'll have a nice and thin illumination. But as you go away from the center, suddenly your beam will start diverging and you will get a thick illumination. So people have come up with other beams like a Bessel beam, Airy beam, and they are non-diffracting beams, but it has some other complications or challenges associated with that. Like in case of Bessel beam, you have a side lobes. So even though you are using for imaging your central beam, but side lobes, they give you a little more phototoxicity. So it helps in some respect, but there is no free lunch. So you sacrifice in terms of phototoxicity. Then there is a lattice light sheet. You might have all heard from Eric Bedjick's group. So basically what they do is they synthesize a 2D lattice. Like from our solid state physics, we all know what lattice is. And they use that discrete illumination to illuminate your plane. But then you need to scan that to cover the entire area. So it has certain advantages. It allows you to mimic or implement SIM type of illumination. I'm not going to go in that, but you all can discuss with Professor Mandal. So one of the challenges in a light sheet is how to improve resolution further. And in this lattice light sheet approach, people have implemented structured illumination microscopy configuration to further improve resolution. So these are some different ways you can create your illumination. And then you have a lens, you put a filter, and you use a wide field detector to get this entire plane. So let's dissect any given light sheet system. Any given light sheet system, you can dissect into 3 components. One component is your illumination. Second component is your sample mounting, because sample mounting and that configuration gives you a sense how these lenses are arranged. And the third component is detection. As you might have seen in lab yesterday, in Professor Mandal's lab, you are doing in this geometry. So you are illuminating like this, and then you are detecting like this. So any light sheet system, basically, you can dissect into 3 major building blocks. And how you create a illumination, basically, you will have a laser, you will have a laser control to turn on, off, or control intensity. And then you need a beam shaping optics, whether you are using cylindrical lens or you are using a galvo mirror or piezo mirror to scan your beam. There are different options of doing that. And then you need another lens, which you can call illumination lens, to basically bring that light at your desired space in your sample chamber. And then you need another lens, which is orthogonal to this illumination lens, to collect that information, because in this case, you are capturing, or you are trying to capture this entire plane at one go and map that on a 2D detector, which is typically nowadays a CMOS camera, scientific CMOS camera. And this configuration, almost 90% of light sheet microscopes are kind of arranged, centered around this configuration. So for this configuration, what you need is you need two lenses, and they need to be orthogonal in geometry, whether you mount like this, or what you saw in Professor Mandal's lab like this. But these two lenses, you need to be in orthogonal geometry. And here long working distance comes into picture, because you need long working distance lenses, otherwise you will get a hindrance. There is not enough real estate to put these lenses in orthogonal geometry. And that's one of the constraints in light sheet microscope, because then we can't use any lens you can get your hands on, or you can't use any high NA lens, because as you start increasing numerical aperture of those lenses, your working distance decreases, and it gets difficult to fit two lenses in this geometry. We will talk about, there are some exceptions now where people have developed single lens light sheet microscope. So we will talk about that little later. I don't expect to remember all of these, but this is just to tell you or show you that there are different configurations. I mean, people have come up with all kinds of possible combinations or geometries you can think of to put these lenses or bring illumination orthogonal to your collection objective. And this is the paper I mentioned in 2008, basically, where you mount your sample. There are a lot of samples you can mount in a capillary. So sample is mounted in a capillary. There are two galvos to scan this beam in Y and also in Z. So basically, by scanning this beam, you are creating a virtual illumination. And then there is this lens, which is collecting this fluorescence and mapping on a detector. And then also you can rotate your sample to get a multi-view. So basically, using the same optics or optical configuration, you can rotate your sample to get a multi-view. For many applications, this is very useful, because if you look at some large embryos like fish or fly or those kind of samples, they're not very optically transparent. So if you illuminate from one side and detect from one side, you don't get to see the other side because of scattering and absorption and all. So in that case, what you do, or what researchers do, is basically you image from one side, rotate it, image from another side, rotate it, another side, and then computationally you can fuse. So basically this allows you to do, in a microscopy jargon, multi-view acquisition. For same sample, you can look at from different perspective, and then computationally you can fuse those images to retrieve more information which any of those views can give you. So, but there are some samples which you can't mount in a capillary, and Dr. Harish Rao, when he started his lab at the NIH, he wanted to do cell biology using light sheet. So he came up with this geometry. Can't we mount these lenses? They are orthogonal, but in a vertical stage, so that you can do your conventional sample prep, whether you want to do cell culture or mount embryo, come from top, and you illuminate from one side and detect from the other side. So that's another way where you can, and these are water dipping lenses. So your sample is sitting in a media, appropriate media, so that your cells are happy. But again, if you pay close attention to this geometry, your illumination and detection, they are orthogonal. And that's why it's like a selective plane illumination configuration. The other aspect I wanted to highlight for any confocal, if you have used confocal microscopes or wide field microscopes, and if you look at the point spread function, you will see that your point spread function is pretty good in XY, but it's more elongated in axial dimension. Or axial dimension, you can, the way you want to define is along the optic axis of your lens. And we can't do much about that, because that's inherent to our lens design. We don't get high frequency components from the axial dimension. So in many cases, our axial resolution is few times worse than the lateral resolution in case of single objective microscopes, so whether it's a confocal or wide field and all. And as you can see in this example, this is XY lateral view of a C. elegans embryo, where you're looking at these cells, and if you look from axial dimension, these cells look a little elongated. Another related problem with the Gaussian beam illumination, as I mentioned earlier, in the center of this beam, you have a nice and thin illumination, but as you go away from center, it gets thick and broad. And that's, again, Gaussian nature of this beam governs. So basically, it depends on your numerical aperture of your input beam. You can control this Rayleigh length, but you have, at some point, you kind of run into this problem. If your sample is large, no matter what, either you end up making your light sheet very thick, or if you want to make it thin, then center is thin, but as you go away from center, it starts getting thicker. So the disadvantage of this is basically part of your sample will be nice, SNR will be good because you are rejecting, to begin with, not much out of focus photons, but part of your sample sees much thick illumination, and then your image quality across the field of view, they are not similar or same. So basically it degrades as you go away from your illumination beam waist. So what are the solutions? I mean, I don't have to go in detail, already we talked about that. I mean, you can use a Bessel beam. So basically you can make your beam non-diffracting, but the downside is you will have the side lobes, so phototoxicity will be more. And same thing you can do using lattice light sheet, basically lattice illumination. So you can synthesize a beam which is thin and across the field of view, but it has also some challenges. As you go in thick samples, your lattice, it doesn't hold same spatial configuration as you are in shallow depth. So as you go deeper and deeper, your lattice illumination gets distorted and your image quality degrades. But this is a good option if you are looking at more thin or small or optically transparent samples. The other thing, I mean, people have implemented is you take a high NA beam, specifically Reto Foelka's group, they demonstrated that you take this high NA beam, and instead of imaging this entire plane, you just follow the beam waist. So basically you just take the information closer to beam waist and disregard all other out of focus light. Again, it slows you down a little bit, but it gives you high quality illumination across the field of view. And also it has a slightly more phototoxicity. And in this particular case, we take advantage of light sheet mode or rolling shutter mode of SCMOS cameras. Most SCMOS cameras, they scientific SCMOS camera, they facilitate that. So what you do is you can control how many pixels you want to be active. So instead of a global acquisition, you do slit scan or rolling shutter mode, and you sync your rolling of these pixels with your illumination beam waist. And this way it works as a virtual confocal slit. Basically you are not detecting, even those photons are hitting your sensor, but you are not accounting for them. And this improves your image quality a little bit. Let's see. I don't know why this animation is not working. It's from Andrew York's lab at Calico, and Kevin Dean, then a graduate student with Reto, they implemented this remote focusing approach. So basically, without moving your lens, which is creating illumination or detecting photons, you can do this kind of a scanning fast remotely, so that you are not putting a lot of movement or stress on your sample. Also, people have implemented electrical tunable lenses, and also there is something called tag lens, acoustic lens. Using acoustic lens also, you can scan beam waist along the optic axis fast. Earlier, I mean, the earlier iterations was limited how far you can go, but lately people have come up with a better electronics, and you can always almost go up to a millimeter. You can scan the beam waist. So basically you can take a high NA lens or high NA Gaussian beam and raster that beam waist along the optic axis fast. Similar approaches also people have implemented using SLM and all. So there are different ways, but overall idea is you just capture the beam width, and as you are scanning that beam width in axial dimension, you reject unwanted photons and just collect the photons which are useful, and this way you can improve your image quality, but at the cost of speed and phototoxicity. I like showing this original paper again from Stelzer's group, where he showed and his team, they showed that if you take a sample and take a multi-view acquisition, and once you fuse that, you retrieve more information. And this is also used commonly in other modalities like MRI and all, people do that. So now it's very common in light sheet microscopes where we take multi-view acquisition and figure out a way to combine those views to get retrieved better information. So we talked about axial resolution, that axial resolution is poor if you use any single lens. But as I told you, a lot of light sheet implementations, they kind of impose that we need two lenses. And depending on choice of your lenses, nothing prevents you to use either one for illumination and detection. So now you can imagine in this drawing, if you have this lens, you are illuminating from side and you are detecting using this. So what is lateral in this particular case? I don't know whether you can see my cursor on the left side. If you switch the role, if you detect from the side and illuminate from the top, that becomes lateral. So what is axial information on the left-hand side for this lens becomes lateral information for the other lens. So basically you have a better information from this side. So if we can figure out to merge these two information smartly, basically we can get information which in many cases better than either one of these. And you can see in this example, like we are looking at diffraction limited beads. So you can see view A means you are illuminating using this lens and collecting using this. So XY pretty good, but XY axial dimension, it's more elongated. But if you illuminate using B and collect using A, which we are calling view B, what is XY for A becomes axial, which is more elongated for B, and what is axial for A becomes XY for B. And once you fuse these images, and of course you have to do some sort of registration and deconvolution, so there are some challenges. I mean, it's not again straightforward, but if you do this fusion smartly, basically you can retrieve more isotropic information. And in many cases, it's useful if you are looking to track a particle in a three-dimensional environment. You have a better resolution to track that particle. So, but again, this requires that you are imaging or dosing your sample twice. Now we have some ways we have implemented some workaround where we just illuminate from one side and capture both views, but that works for optically transparent and small samples, not for large samples. And if you do that, here is another example of C. elegans. I mean, if you combine those, you get more information, three-dimensional information. The other artifact or image kind of degradation you will notice if you look at samples which has a lot of absorbing or scattering centers. So you will see this shadowing because your illumination is coming from side. So if there is a particle which either scatters or absorbs, then you are not going to illuminate anything behind that. And there are different ways like Jan Houston's and all, they implemented this pivoting of this beam. So basically you take this illumination and you tilt this illumination very fast. And the average effect of that minimizes some of these shadowing effect. And again, there are other approaches where you can illuminate from both sides. And that's also nowadays very common, and detect from both sides. So this is one of the early implementations of dye SPIM. And the reason I wanted to show you is we spent that time a lot of time because there were not many commercial options except JICE. But we wanted the system to be easily accessible by for biologists. So we kind of miniaturized or made it compact. I mean, still it's not very user friendly. I will accept that fact, but it allowed a lot of biological labs to basically get these parts and build this system so that they can do light sheet imaging. And what we did in this case is, instead of having a bunch of galvos and all, we condensed this in collaboration with ASI using a MEMS mirror. So it's a 2-axis mirror, which is low mass, and it can give you a capability to scan your beam fast. So it gives you capability to scan in a y direction to create a virtual illumination, and also the other axis you can use to move your beam for third dimension Z or Z. So basically this allowed us to make it a compact laser scanner or illuminator for doing this sheet-like illumination. I will skip that, but this allowed, you can see we are comparing. This is acquired on our dye SPIM system, and this is a confocal, spinning disk confocal. Here you can see the cell is still live and things are moving. Photo bleaching is less, while on confocal it's already bleached. And this demonstrates you speed, because we can capture it at fast speed. Basically, you can capture all this membrane ruffling. I'm not going to go in details, but this is just to, so I don't know how many of you are cell biologists or developmental biologists in this audience, but this is just to show that how some of these implementations have enabled us to capture, which was not possible otherwise. This is more on the technical side. I mean, you can do optical scan. This is just an example to show you, instead of doing optical scan, you can also do sample scan. So basically you can park your illumination, you can park your detection, and that's what, if you recall, you are doing in this microfluidics device where your illumination and detection is fixed and you are passing samples through that. So it has certain advantages. Here you can see in this large and extended samples, basically you get good or bad similar image quality across this field of view. So this is basically, I told you so far everything about light sheet systems, and these systems comprises 2 lenses, but I promised you that I'll show you some examples where people have built single objective light sheet system. And I would encourage you all to read this classic paper from Dunsby's group, which was published in 2008. And he demonstrated, and he has done a very detailed calculations also to show the limitations of these systems. And basically what he demonstrated is you can use a same lens. Part of this lens you can use to bring a light, and the other part of this lens, basically, so you illuminate your sample at an inclined plane, and then other part of this lens you use to collect that information. But what happens is, since your image plane is rotated, you can't just project this on a 2D plane. So you need to rotate this plane so that you can, and that's why he has another pair of lenses here to basically rotate this image plane so that he can map on this 2D detector. So it's great, it works beautifully, but the limitation is because of this lens L6 and L7 arrangement. You don't capture the full NA of your primary lens. What they call the first lens is a primary lens. And then Hillman group and all, I mean, they improved this and implemented and showed a lot of biological applications of this technique. But Binyang at UCSF recently showed that you can improve that numerical aperture instead of using an air lens, if you use a water lens. And they figured out this combination of 2 lenses, which gives you slightly higher NA. So suddenly in these cases, your collection numerical aperture was roughly around 0.5 or 0.55. You go close to 1, which is a big improvement. And then Andrew York at Calico, basically, he designed this lens, which they call snouty lens. So basically, it has a weird angle at the front face of this lens, and they use this high index material. So this allows you to, it simplifies your system, because now you don't have to design a water chamber or anything, because this works in air. And they designed a lens combination which allows you to capture highest NA possible from your primary lens. And in this case, they have pushed this limit to go almost close to 1.25, which is for many applications, it's I think pretty good. And then Loic and all, you might have seen a recent paper, and Andrew York, they redesigned this lens to basically capture a large field of view. There are other examples of also single view lens. Paul Maddox at UNC, now he has a company. So what he does is, in his case, basically you can take any confocal or turf system and use a high NA lens, and he illuminates samples from side at slight 2.8 degrees angle. So your illumination is slightly inclined, but you can utilize high NA lens for detection. Same Anna Karin from Bill Moyner's group, now she has her lab at Rice. She did a similar approach where she used this prism to bring this inclined sort of illumination and use high NA detection lens to do super resolution imaging in a light sheet mode. There is another implementation where people fabricated micro mirrors basically in PMMA, and they used, this is a French group, Galland et al. And you can use the same lens to bring your beam, Gaussian beam, reflect from this mirror. So basically it gives you orthogonal illumination and detect it using the same lens. So basically, again, I mean, sample mounting and all, I mean, so as I said, there is no free lunch. So these type of implementations offer you some capabilities, and but also at the cost of some other restrictions. So we need to be aware of, because we know our biological questions and sample better than anybody else. So basically you need to figure it out, what type of sample mounting you need, and what kind of information you need to extract. And based on that, you go to see which sort of implementation is more suited for that. In Hari's lab, we also implemented this 3-view system, because we said that, I mean, photons are emitted in all 4 pi solid angle, and we were doing illumination and detection from top, but also you can capture some of those lost photons from below. And once you fuse all these things, then you gain a little bit improvement in your image quality, both resolution and collection. But again, these type of implementations come at a cost, computational complexity and hardware complexity. So we need to evaluate the gain. Is it worth taking all these headache or taking all this extra work? For many cases, yes, it is, but for many cases, in my opinion, it's not. So we have to be mindful of that. Then again, 4 lens things. I mean, like in Philip Keller's group at Genelia, they illuminate from 4 directions and capture from 4 directions. And also Kate McDowell at MRC in UK, she has also implemented this system. So basically you can illuminate your sample from all directions and collect from all directions simultaneously. And other, I mean, they have implemented autofocus and all, which improves basically as you go deeper and deeper. You don't keep your detection lens same, you tune accordingly so that you can keep it in focus, because some of these samples, you might realize they are optically very inhomogeneous. They are not optical environment is not same. So your light, depending on where you are landing, it can get distorted. And so there are some tricks we all play, and including adaptive optics and all to go around that. So basically you have a 4 lens system where you can do multi-view acquisition. In Hari's lab also, we had implemented a 4-view, and the way we had done this was more for thin samples. Like we took a mirrored glass and you mount your sample there. And when you come from top, that beam reflects because you have a mirror at 45 degrees. So you get 2 illumination and 4 detection simultaneously. And this way you get a pseudo 4-view detection. But again, then you need computational approaches to fuse those views, and so it gets a little complicated, but that's another variant of 4-view system. So with that, I mean, basically, I hope I convinced you light sheet system is very powerful for many applications. Depending on your biological applications or material science application, you configure your system and you decide what sort of configuration is more suited or well suited for you. What are the future prospects? Intentionally, again, to not make it redundant, I'm not going to talk about what Professor Mandal talked to you all yesterday. Lithography, I mean, certainly his lab has pioneered that approach, and recent work from his lab where you can use for planar or line trap of particles. So those applications are certainly there. But what we are also interested in is expanding the information space. So with my collaborators, we are also working on, can we get orientation information in a light sheet mode about molecules, single molecules or ensemble of molecules. And we have taken a different approaches, because I'll be happy to talk in detail, but if you look at orientation, there are a lot of degeneracies. It's if you plot on a sphere, you'll see that depending on how molecules are oriented, there are a lot of degeneracies. And again, a SPIM system is ideal because you can capture from different directions to break some of those degeneracies. So we have successfully implemented it, but there are still a lot of challenges about the retrieving that orientational information and data fusion and all, which we are working on. Another approach basically do multi-channel polarization imaging, which is going on in collaboration with Paul and his lab people, where we want to illuminate from side, but use high NA lens and do 4 orientation measurement, as you can see in this schematic, simultaneously, so that we can get an intensity, basically gives you position information, and also these 4 simultaneous channel measurement gives you orientation information. So you can compute what is the location of this particle and how it's oriented, because many of these emitters, they behave as a dipole. So we want to know how this emission dipole is oriented. So, and of course, I mean, I didn't get a chance to talk about spectral imaging and all. There are a lot of good work done from Husken's group and Scott Fraser's group, and so spectral, I mean, people have done. Also, you will see there is another field called light field imaging. So that also people are trying to combine this light field concept where you can take the entire 3D volume at one go. So that's another field. But again, that comes with a massive data and computational challenges. So with that, I just wanted to highlight some of these things you need to think through when you are deciding. A lot of times we get excited that, hey, this is a cool system, this is a good system, this will solve all my problems. I mean, that's not true. So basically, you have to take a step back, think about your problem, do some confocal imaging, and evaluate what exactly you need for your biology to answer your biological questions. And then you see what are challenges you have. If you have access to a light sheet system, can you mount your sample? Even the system is very good or fancy, if you can't mount your sample, it's no good for you. So you need to evaluate that. What is detection NA of that lens? If you are looking to get high resolution information, if detection NA is pretty low, 0.3 or 0.8, that may not be adequate or sufficient for your application. So what is light sheet thickness? If your sample is thin, but your light sheet is thick, it's no more light sheet, it's a wide field. So these things you need to address. Do you need just lateral resolution, or you want to look to retrieve more isotropic information so that you can do particle tracking? I say that if you don't take extra data, because any extra data you take, that's a burden and headache for you. And that's what it comes. Do you need multi-view? If you don't need, there is no point of taking multi-view. Also, you need to keep in mind what is volumetric speed, because for many cases, if you are doing a time lapse, you want to capture 3D with time, so you want a volumetric speed. What is effective field of view? If my sample is 1 millimeter, if I get 100 micron image, then that's not going to work, because then I'll have to take several of those images and do the tiling. So that is going to slow me down. So what is typical data size? Can I handle this data? I mean, if you acquire this data and it takes you a week or months to just access the data, I mean, it's better not to have that data. So some of these practical aspects I would encourage you to think through when you are deciding what system you are going to use and whether that is adequate or sufficient to answer your biological questions. Here I will end. Sorry, I'm almost close to 11, sorry, midnight here. So, but I would like to thank a lot of my collaborators and funding agencies, and I'll be happy to take questions if there is any.
Yeah, I think, yeah, Abhishek is done kind of. So, a great talk, Abhishek. It's a great tutorial talk and much suited for workshop, and specifically that you talked about application specific thoughts are really wonderful, because those are the practical aspects that we need to look at. And yeah, of course, some of the images that you've shown on the front page, were actually for the first time I've seen something like that about the C elegance. And okay, it's good for beginners and students, and hopefully we'll have you physically next year in our workshop.
I will look forward to.
Yes.
But if they have any questions, I mean, feel
Yeah,
free
yeah,
to email me.
we'll go through that. So we have time. So let's have some questions. So now it is open for questions. So can you some of the audience, if they can ask, they want to ask some questions, please go ahead.
Yeah, I see one question in chat window.
Okay, please, what's the question? 1 minute, hold on.
You want me to repeat, or?
Okay, with light sheet. Okay, so with light sheet, while scanning a sample, what step size we can expect? Okay, this is a question.
That's a good question. I mean, you need to do, I mean, what we call, it's not really Nyquist, but you need to do enough sampling so that you don't have a missing gap. I mean, if I take a bigger steps, so I have information here, then there is a missing information, then there is information here. So what you want to ensure is, depending on your light sheet thickness, that there is an overlap in each plane, so that when you put it together, you have a continuous information space. So it's governed by your light sheet thickness primarily. But in many cases, when people are doing calcium imaging and all, they sacrifice this information a little bit because they want to capture volumetric speed fast. They don't care about whether you are getting all the information. What they care is, can I get some of this information very fast? So in that case, what they do is they do what we call is a coarse sampling. So I'll say that if your light sheet thickness is around 1 micron, probably you want to do 600, 700 nanometer steps, so that when you go through this 3D, you will have a continuous, or if you average those, you will have a uniform illumination in entire voxel. So that's a good question. It also depends on what is your depth of focus of your detection lens. Accordingly, basically, we tune the light sheet thickness. If I'm using low NA lens, there is no point of making, if my depth of focus is 3-4 micron, there is no point of making very thin light sheet. So that's a great question.
Yeah, thank you, Abhishek. So any more questions you have? You can write, you can chat, or you can actually directly ask.
Sorry, I can't hear from the classroom.
Audiences, one question.
Yeah, go ahead.
Hello, sir. Can you hear me?
Please call me Abhishek. Yeah, sorry. just repeat. Repeat your question, please.
Sir, it was quite a good talk. So
thank you.
I just wanted to ask you, like, regarding the light sheet microscopy, like, what are the major drawbacks that you think that light sheet has to overcome to become much more full-fledged compared to other microscopic techniques?
Yeah, that's a good question. And may I know what you work with? I mean, are you a tool developer, physicist, optical engineer, or application? You come from an application background, a biologist, or?
Sir, basically, I'm a chemist. So I'm quite interested in working in a single molecule level microscopic techniques. So I'm quite interested in new techniques to learn also.
Okay, great. Yeah, so that's so one of the challenges, in my opinion, is As you know, for confocal, you can put a highest NA possible. Like you can go to 1.49 routinely, people can go. Now there are some lenses you can go to even 1.68. So forget about 1.68. If I can put a 1.4 or 1.49 lens on a light shade system, I'll be very happy for single molecule or this kind of thin samples. The other thing is still, it's not well implemented. I mean, we all have tried in a different flavors. If we can combine structured illumination with a light sheet using high NA lens, that will help us in some way. Basically, then with the diffraction limited imaging, because light sheet is gentle, if we can sacrifice a little bit imaging time and phototoxicity, but that will take us resolution a little bit higher dimension or a higher number. So that will be useful. But again, there are challenges people have implemented, but since we are using a beam, or so you get resolution enhancement in one dimension, so it gets more complicated. And again, to begin with, if my numerical aperture is not high, even I implement all these things, I'm not going to gain much. So that's why the single objective work from Andrew York and Reto Falca's group, I mean, that's very encouraging because they have pushed this envelope of using a slightly higher NA or utilizing the high NA aspect of a single lens system. So in my opinion, if we can go higher NA and implement structured illumination microscopy, 3D structured illumination microscopy, let's call it, that will be a big step forward. And the reason I'm saying is SIM, again, Professor Mandal will disagree because he does a lot of single molecule. I mean, that's a great technique, but SIM allows you to use any chromophore, any sample. As long as you can see photons, you can do structured illumination. So that gives you flexibility. So people have done single molecule with light sheet, including Professor Mandal's lab. So that's been demonstrated. But if we can increase numerical aperture and combine it with SIM efficiently, that will take us to a next level. The other thing, since you asked, I mean, but it's not relevant to your application, but there are a lot of applications where people are interested in imaging cleared brain, mouse brain, or rat brain. And those samples are big compared to length scale we are talking about. And there also light sheet is proving more useful. And there are many commercial systems, and there are, you can see, even though those samples are fixed, but this is speed aspect of imaging gives you some leverage. So basically what 1 centimeter volume sample I can image on confocal, it will take me a month. On a light sheet configuration, you can image that in probably a day or less than a day. So that aspect is also people are utilizing nowadays a lot. But for your specific application, I think high NA and also probably going label free. There are some papers recently and where people are looking at Raman signal or reflectance or scattering. So those things will be more valuable if we can merge some other modalities in this configuration. I think that will be useful. I mean, sorry, I probably didn't give you a direct answer, but some of these are challenges we are all facing together. Yeah.
Right.
Another one student have.
Yeah. Go ahead.
So could you go to the slide where you first introduced inverted SPIM?
Okay. Yes. Yeah. Let me. Oops. Okay. Where is my slides? Which one? This one. This slide. Can you see that?
No, one where it
Okay.
shows the cameras and the detectors.
This one?
No.
This one? No.
No, sir, it would be the inverted SPIM.
This one?
Yes, sir.
Yeah.
Sir, I just wanted to know what's the function of the second camera below.
Oh, so second camera, I mean, typically, I mean, the way initially we had configured is basically we use a low mag lens so that you can find your sample. As you can see, it's a weird geometry, 45 degree. And a lot of times scouting around your sample is a little difficult. So what we do is we align these two lenses with the third one, and you put a low mag lens and not so expensive camera to find your sample. But later on, as I showed you, a 3-view system. Basically, what we did is we use this lens, we put a high NA lens and a better camera to capture 3 views and fuse them together. So I mean, it's just for ease. Yeah, thanks. That's a good point. Basically, so I mean, the idea is to show you that, I mean, you can mount all these things in a different way, and depending on what information you want to extract, basically you can utilize accordingly. Thanks. Yeah.
Yeah, Jigme, any more question that the audience have? I didn't hear anything. So yeah, maybe there are no more questions, but you know, Abhishek, I want to ask a question, and that is something to do with your axial scan illumination. So I just want to know how fast people can go. Like, this is a wonderful thing, like your illumination, you know, scanning along axially, which is little rare, which is a bit rare as compared to XY. So how fast and how efficient it is when we compare to our existing.
It's, I mean, we have also implemented, it's pretty efficient. That's a very good point. So what Professor Mandal is asking about this aspect. So he's saying is because we need to scan this in axial dimension. So it depends on how far you want to go. If you want to go 100 micron and all, I mean, typically we are limited by the camera speed, because all these cameras, if you are looking to read few rows, you are limited by that speed, because other mechanical hardware can go faster. The other limitation I will say is sometimes even your camera is fast, you can mechanically scan this fast, but you need enough photons. If you don't get enough photons from your sample, then even you can go fast, I mean, it doesn't help you. So that's another limitation. So I would also urge you all to read a little more about SCMOS camera and understand that, because that will help you understand different configurations people have implemented. We are really utilizing some of the flexibility SCMOS cameras and their control electronics is providing us. So, and now, I mean, it's hard to get a good EMCCD, because all camera manufacturers, they are imposing that we should buy SCMOS. So I would urge you all to read a little bit about SCMOS architecture and electronics, and how different modes, I mean, that will help you understand when you are using any system, you can basically gauge what mode of acquisition you should use, which is better suited for you. Thanks. That's a good question. Sorry, I glossed over a lot of things, I mean, in this talk, but
No, I think they're quite enlightened by the talk, and this is very student-friendly talk where they can understand.
Thank you. You are always kind.
Yeah. So I will not hold you up, but I think there are no more questions. So please, it's already night, and thank you. Thanks for taking up the time at midnight.
No, thank you all. It was a great honor. Yeah, thank you all being part of this, even virtually. Yeah, thank you.
Okay, I think thanks a lot. Yeah. Okay, so we'll end the talk, and you know, we'll go ahead with the other part of the workshop. Thanks a lot, Abhishek. Thanks.
Enjoy your workshop and learn as much as you all can. You are in good hands. So, and I look forward to hearing from you all. Anytime, feel free to shoot us emails. Okay.
Okay. Thank you. Thank you.
Have a good day. Thanks. Yeah.